Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Today we are going to discuss electrochemistry, lecture 4. In the previous class, we discussed about electrode potential, Nernst equation, and problems related to electrode potential and Nernst equation. Now, in this lecture, we'll discuss some more types of electrodes. So, what are the different types of half-cell electrodes we have? Metal, metal ion type, gas ion type, metal insoluble salt anion type, and redox type. These are the 4 electrodes, half-cell electrodes we have. And what is metal, metal ion type, gas ion type, metal insoluble salt anion type, and redox type? So based on this, you may get objective, but till now they have never asked any questions based on this concept. But still it is there in the syllabus, so we have to discuss. Next, what is metal, metal ion type? So silver solid, silver ion gains 1 electron and forms silver ion, changes to silver. That is called reduction electrode. Since silver ion is gaining to silver, silver ion is changing to silver by gaining 1 electron, it is called metal metal ion type electrode. It is called metal metal ion type electrode, also called as reduction electrode, because reduction is taking place, that is gaining of 1 electron. So silver ion changes to silver is called metal metal ion type electrode. Next, gas ion type. So here, whenever we are, when very important point here, you have to note down. See, whenever you are writing hydrogen gas, we have to use an inert element, that is platinum, because hydrogen gets absorbed on platinum surface. So that's why we are, whenever you are using gas, we have to use inert electrodes, that is platinum. So here platinum H2 H plus oxidation electrode. Here hydrogen changes from 0 to +1. So 0 to +1 is increase in oxidation number. Increase in oxidation number is called oxidation electrode. So half H2, 1 atmosphere changes to H plus electron. This can act as reference electrode. And second one is example of second one, gas ion type, platinum Cl2. See here again, why PT is being kept there? Because of gas is, whenever you are representing gas in a galvanic cell, we have to definitely write platinum over there, because it is inert electrode. So Cl2 changes to Cl minus. This is also oxidation, because Cl2 chlorine 0 changes to 0 minus 1. So it is -1. So here decrease in oxidation number. So it 0 to changes to -1. So it is nothing but by gaining electron, it is called reduction electrode. So this is called gas ion type electrode. Next, metal insoluble salt anion type. It consisting of a pure silver wire sheet in a solution of potassium chloride saturated with solid silver chloride. So it consists of a pure silver wire sheet in a solution of potassium chloride saturated with solid silver chloride solution. So solid silver chloride, sorry. Next, electrode representation, how it represent silver solid silver chloride changes to Cl minus ion, 1 molarity, and cathode reaction is silver chloride gains 1 electron and forms silver plus chlorine ion. So this is called metal insoluble salt anion type. Just only these are nothing but, it is not there in the syllabus also, only additional material. Till now, they never ask questions based on this. So no need to worry about it. Just they are showing different types of electrodes. Next, we have calomel electrode. It consisting of mercury covered with mercurous chloride in contact with a solution of potassium chloride. So mercurous chloride and solution with potassium chloride consisting of mercury covered with this. This is called calomel electrode. Calomel electrode. So electrode representation, mercurous chloride changes to Cl minus salt bridge, and cathode reaction H2 to Cl2 gains 2 electrons. So this is also a reduction electrode, because it is gaining electrons. So it is also reduction electrode. So these are the different types of electrodes we have. Next, we have quinohydron half cell electrode. It is an equimolar mixture of benzoquinone and hydroquinone. So what is the electrode representation? Platinum quinohydron H plus. So cathode reaction, it is quinone plus 2H plus gives us to quinol. Quinone, quinol. Here non means ketones group and ol means alcohol group. So quinone to quinol. Quinone to quinol. NONE. It is a ketone group and changes to quinol, alcohol group, NOL. That's it. So hydroxyanthocquinone, or you can say quinol. Next, clearing the diagram. Yes. Platinum is dipped in an electrode system containing ions of an element in more than one oxygen state. That is called ion plus 2 to plus 3. So here Fe plus 3 gains one electron and forms Fe plus 2. So this is called cathode reaction. That is called redox half cell. Half cell reaction already we know. If we take either oxidation or reduction, half of the reaction is nothing but redox half reaction or redox half cells. And this is nothing but it is constructed by using platinum wire dipped in an electrode system containing ions of an element in more than one oxygen state. So ion exhibits plus 3 oxygen state, we'll call it as ferric, and plus 2 oxygen state, we'll call it as ferrous. So that's why we'll say Fe plus 2 to Fe plus 3, and Fe plus 3 changes to game. Next concept recap. What is Nernst equation? In the previous lecture we have discussed. So for single electrode, Nernst equation is very, very important. Note down. Plus you will get here. E degree of Mn plus changes to Mn plus changes to M plus 0.059 by 1 plus 0.059 by 1 into log of Mn plus. So this is log of concentration of Mn plus is the equation for finding Nernst equation of single electrode. Single electrode, we have to use the formula. This formula is very important. You can see this is Nernst equation for galvanic cells. Is already we know E degree of EMF of the cell is equal to E degree of cell minus 0.059 by N into log Q. And very, very important, the relation between equilibrium constant and standard EMF is E degree of cell is equal to, because at equilibrium, here I'm writing, just note it down, at equilibrium, E of cell becomes 0. E of cell becomes 0. So since E of cell is equal to 0, so EDQ of cell comes to this side, then minus minus gets cancelled. So this becomes, the equation is EDQ of cell is equal to 0.059 by N, fine n 1 by N into log base 10 Kc, that is equilibrium constant. In this way, we'll find equilibrium constant by using Nernst equation. And Nernst equation for single electrode. Previous lecture, we have learned what is Nernst equation for a cell. Now, in this lecture, we have given Nernst equation for single electrode. Nernst equation for single electrode is, the formula is what? E of Mn plus 2 mm is equal to EDK of, that is EMF of the cell is equal to standard electrode potential of the cell plus 0. Plus is important here, 0.059 by N into log of Mn plus, concentration of Mn plus, because in this only single electrode is there. I hope it is clear. Next. Now questions based on this. So here it is given, a galvanic cell is constructed with Ag plus Ag and Fe plus 3 to Fe plus 2. Find the concentration of Ag plus at which the EMF of the cell is 0 and concentration of Fe plus 2 and Fe plus 3 are same. The standard electrode potentials are given, and they are asking us to find concentration of silver plus. And here they are given EMF of the cell is 0, means E is equal to 0. So first in this question, we have to find, by joining these two cells, by joining silver and iron, we have to find out electrode potential of the cell. So after finding that, we can straight away find out the concentration of silver ions by using Nernst equation. So let us see how we will do. This is lengthy problem, so I'm taking one more slide. So you can see here what is given, everything I'm writing here. So first we have Ag plus 2 Ag, Ag plus 2 Ag, that is E degree of Ag plus 2 Ag, E degree, E degree of Ag plus 2 Ag is equal to plus 0.8 volts. Second, E degree of Fe plus 3 to Fe plus 2 is equal to, both the reduction potentials is equal to 0.77 volts. Now, from these two data, they are asking us EMF of the cell is equal to E degree of cell minus 0.059 by N into log of, by N, that is 1. Here N is nothing but 1. into log of 1 by Ag plus, because the concentration of Fe plus is equal to concentration of Fe. So they are given. So just we have to take this consideration. And first, before going to this, we have to find first EDK of cell. So EDK of cell is equal to 0.8 minus 0.77. Why? Because 0.8 more positive value cathode and less positive value anode. So it is nothing but cathode minus anode. It is 0.03 volts. So EDK of cell is equal to 0.03. Since EMF of the cell is equal to 0, since EMF capital E is equal to 0, we can write the further equation. E is equal to 0 implies EDK of cell is equal to 0.059 by 1 into log of 1 by concentration of H plus Ag plus. We have to find that. Why we have taken 1 by concentration of Ag plus? Because concentration of Fe plus 3 is equal to concentration of Fe plus 2. It is already mentioned in the numerical. So by this we can write 0.03 is equal to 0.059 by 1 into log of 1 by Ag plus. So that is equal to log of 1 by Ag plus is equal to log of 1 by Ag plus. Concentration of Ag plus is equal to 0.03 by 0.059. So which is equal to 0.508. So 0.508 means nothing but log 3.1 value, because log 3 value is 0.4771. So 0.508 means log 3.1 value. So concentration of Ag plus is equal to log of concentration of 1 by Ag plus is equal to log 3.1. So concentration of Ag plus is equal to 1 by 3.1, which is equal to 0.31. Here one more step is missing. Concentration of log of 1 by Ag plus is equal to log of 3.1. Log cancels on both sides. So 1 by Ag plus is equal to concentration of Ag plus becomes 1 by 3.1, which is equal to 0.31 approximately. So 0.31 molarity. So in this way you have to find this numerical. I hope it is clear. So answer is 0.31 molarity. So again, I will explain this question in theoretical manner. So it is constructed, galvanic cell is constructed by the means of Ag and iron. So silver and iron. And in this, iron is taken as anode because 0.77 volts, that is less positive value when compared to silver 0.8 volts. So lesser positive value should be taken as anode and greater positive value should be taken as cathode. And both they are given reduction potentials only, and there is one electron change. Ag plus 2, Ag 0, that is one electron change. Fe plus E2, Fe plus 2 also one electron change. So by substituting that, and they are given here, the EMF of the cell is 0. So total E is equal to 0 by constructing these two. By joining these two cells, they have called it as EMF of the cell is becomes 0. Then what is the concentration of silver plus ion? So taking that into consideration, we have found out the answer. So I hope it is clear. Next. Zinc granules are added to 500 ml of 1 molar nickel nitrate solution at 298 kelvins until equilibrium is reached. Calculate the concentration of Na plus 2 at equilibrium. The standard electrode potentials are given. So first we need to add these two, because by joining these two cells, we will get EDK of cell, and they are asking us to calculate the concentration of Na plus 2 ion at equilibrium. And at equilibrium, we already know that EMF of the cell is equal to 0. At equilibrium, we already know that EMF of the cell is equal to 0. So here also I'm doing again the problem. So you can see here now how to solve this problem. Given what? For 500 ml of 1 molar T and a nickel nitrate is just they are given for confusing us. No need to take that 500 ml. So EDK of Zn plus 2 to Zn is equal to, since at equilibrium, first condition is at equilibrium, EMF of the cell is equal to 0. That is first point. Next, first you have to find EDK of cell. Then EDK of cell is equal to 0.059 by 2 0.059 by n. Here 2 I am directly writing, but n if you write it's better. Into log of concentration of Na plus 2. Yes, concentration of Na plus 2. So we can take, because here EMF of the cell is equal. So EDK of cell is equal to 0.059 by 2. So first EDK of cell we have to find by adding zinc and this thing. So 0.04 minus of minus 0.76, because zinc becomes anode, nickel becomes cathode. So it becomes 0.24 plus 0.76, which is equal to 0.52 volts. Next, substituting this 0.52 is equal to, because zinc is given 1 molarity, so no need to write that. So log of Na plus 2. So by substituting this, you'll get log of Na plus 2 is equal to, directly I'm writing the value, log of Na plus 2 is equal to 17.62 is equal to 17.62. Concentration of Na plus 2 is equal to 17.62. So only concentration of Na plus 2 we have to take. So concentration of Na plus 2 is equal to anti-log of 17.62, because log is nothing but anti-log. If you go that side, it becomes anti-log. So when you are writing anti-log, just 17.62 that will come as 10 power. So answer will be 3.164 and 10 to the power of minus 18. M, capital M. So this is the molarity of nitrate solution. I hope it is clear. Next. So 3.164 and 10 to the power of minus 18 molarity. Next. So these are the important models in Nernst equation. Next we'll see next topic in these questions. So what is the relation between standard EMF and standard free energy change? What is free energy change? For every reaction or whatever the process, if you take physical process, chemical process means you'll take reaction. Physical process means you'll take the experiment. So for any process, if there is any change in the process, means nothing but here chemical energy. In chemical process, what happens? Reactants change to products. So as the reactants are changing to products, so what happens here? Either ions or products directly also. There is a free energy. The energy is called as free energy change. Free energy change, and it's denoted by letter delta G. So standard EMF and the standard free energy change are related as delta G degree is equal to minus NF E degree of cell. Minus NF E degree of cell, where E degree of cell is nothing but electrode potential of the cell, not the EMF of the cell. So delta G is equal to minus NF E degree of cell. Similarly, the standard free energy change and the equilibrium constant are related as delta G is equal to minus 2.303 RT log base 10K, where R is called gas constant, T is called temperature. So these two formulas are very, very important. So the standard EMF and the standard free energy change are related as delta G is equal to delta G degree is equal to minus NF E degree of cell. What is delta G degree? It is called standard free energy change. It is also called as Gibbs energy, Gibbs free energy. So the standard free energy change and equilibrium constant are related as delta G is equal to minus 2.303 log based in Kc. So these two formulas are most important. Based on these formulas, they will definitely ask questions in the examination, competitive exams. So how we'll get questions based on this? Easy it is. Very, very important also. Next. The Nernst equation recap here we are doing. So the Nernst equation for a cell is given by E of the cell, that is EMF of the cell is equal to EDQ of cell minus 0.059 by N into log Q. At equilibrium, is EDQ of cell, that is EMF of the cell is equal to 0. Already we discussed. So Q becomes K, and by this you can write EDQ of cell is equal to 0.059 by N log K. In general, at any temperature, the standard EMF and equilibrium constant are related as EDK of cell is equal to RTNF natural logarithm K, and EDK of cell is equal to 2.303 by and 2.303 RT by NF log K. So these are the formulas. Now we are going to apply these formulas in the numericals. Very, very important. This is a simple question. Calculate the equilibrium constant for the reaction at 298 kelvin. This is NCRT based question. So sometimes they give directly NCRT based questions also at 298 kelvin. Temperature is only the mandatory. And here we have to calculate EDK of cell at 298 kelvins. So first in this question, what we have to do first, we have to find EDK of cell by joining zinc and copper couple. So zinc and copper if you have to join, and already we know zinc is anode and copper is cathode. So EDK of cell is equal to EDK of cell is equal to EDK of that is EDK of oxidation potential 0.34, that is cathode minus 0.076 anode, which is equal to 1.10 volts. Now, what is the relation between EDK of cell and log, that is equilibrium constant? So EDK of cell is equal to 0.059 by N, that is 2 electron into log base 10 Kc. Log base 10, no need to write base 10, just simply you can write Kc. So now we have to find log Kc only. First we'll take log Kc is equal to 1.10 into 2 divided by 0.059, which is coming around 37.28. So Kc is equal to anti-log of 37.28. So when you are writing anti-log, definitely that 37 will come as 10 power. So anti-log of, and remaining value not to remember, because anyway from the options we can see. So anti-log of 37.28 is equal to 1.65 into 10 to the power of 37. So only the, remember, they will not give anti-log values in the examination, but still you can take the decimal before decimal 37 is there, that will come as 10 power. Very, very important. So in the options, wherever you have only one option, they'll give as 10 power 37. Remaining all options, they'll give differently. And 1.65 is anyway, we can do it because 10 power 36 is our, 10 power 37 is our identification. So I hope it is clear. So in this way, we have to find equilibrium constant from the electrode potential of the cell. So electrode potential of the cell is equal to 0.059 by N into log base 10 Kc is the formula for finding electrode potential, and at equilibrium EMF of the cell becomes zero. That's from that way, that's from that relation only we got electrode potential of the cell is equal to 0.059 by N log base 10 Kc. I hope it is clear. Next question. So answer is 1.65 10 to the power 37. Next, the standard EMF of a Daniel cell is 1.1 volt. They have given directly EMF of the cell, that is EDK of the cell. EDK of cell is equal to 1.1 volt, and they are asking us to find calculate standard free energy cell, standard free energy of the cell reaction. So delta G degree is equal to minus G degree is equal to minus NF EDK of cell. So here 2 electron change, because already we know Daniel cell is consisting of 2 electron change. So it is equal to minus 2 into F value, that is 96,500, into EDK of cell, that is 1.1 given already. And whatever the answer you'll get after multiplication, you'll get the answer in joules, but they'll give in the answer in kilojoules. So this is this many joules. So finally delta G degree is equal to minus 2123. Minus should be there. Minus 2123. 212.3 kilojoules per mole. So that is kilojoules, that's all. So definitely they'll give you the answer in kilojoules. You have to convert, that is by divided by 1000. If you do 212300 by 1000, you'll get in kilojoules. That is very simple, already you know, I think. So this is the question related to standard free energy change. I hope it is clear, this direct question. Next, the standard EMF of the following reaction is given 0.3236 volts. Calculate the standard free energy change and equilibrium constant. So they're asking both. And the reaction is given 2 Fe plus 2 iodine minus 2 Fe plus 2 plus iodine. So it is 1 electron change or 2 electron change. It is 2 electron change by clearly seeing that. Simple. So they are asking us to find both delta G as well as equilibrium constant. So straight away the formula delta G is equal to, I'm taking new slide. So delta G in this question is delta G is equal to minus NF E decay of cell. Delta G is equal to minus NF E decay of cell. That is because E decay of cell is given 0.236 volts. So minus NF E decay of cell, and is 2 electron change because 2 iodine minus is given. So minus 2 into 96,500 into E decay of cell is given 0.236, that is EMF of the cell is given. Now by this we can write is equal to minus 548 joules, minus 548 joules. Next, they are asking us also to find out E decay of cell is given is equal to 0.059 by N into log base 10 Kc, because they are asking us to find equilibrium constant. So we can write log base 10 Kc is equal to 0.236 into 2 by 0.059, which is equal to 8. So Kc is equal to antilog of 8. So only after 8 nothing is there. So we'll take 10 to the power of 7 antilog of 8. So Kc becomes 9.54 into 10 to the power of 7. So for this type of questions, we have to identify where 10 to the power of 7 is given. After 8 point, if 8 is increased, then automatically 10 power 8 will come. Since it is equal to 8, so straight away we'll write 10 to the power of minus 10 to the power of 7. I hope it is clear. I hope it is clear. So answer delta G decay is equal to minus 45,548 joules, and Kc is equal to 9.54 into 10 to the power of 7. Kc is equal to 9.54 into 10 to the power of 7. So these are the problems, very, very important. From Reynolds equation, we can find delta G values as well as equilibrium constant. One more important model is there based on delta G that we'll discuss later. And now we'll move to next topic. So application of EDK values products of electrolysis, very, very important. So the product of electrolysis depends upon the nature of electrolyte. The product of electrolysis depends on the nature of the electrolyte and the electrodes is used. The product of electrolysis of an electrolyte in solution state and molten state may differ from each other. As I told you, they will ask us to find the which is formed at anode, which is formed at cathode from electrolysis. I told you that in the first lecture itself. I told that this discussion we'll do in the last. Now we are doing the discussion now. Very, very important discussion. The products of electrolysis depends on the nature of electrolytes and the electrodes used. Without knowing electrodes, we cannot go. That's why we are done like this. And the products of electrolysis of an electrolyte in a solution and molten state may differ from each other. So already we know in the electrolysis process, if you know, you see, we know cations goes to cathode, anions goes to anode. So, and where at cathode, what happens? Reduction takes place. At anode, oxidation takes place. So, what is formed at cathode? What is formed at anode? That we are going to discuss right now. And topic is very important for NEET as well as JMAs, because they'll give, suppose molten sodium chloride is molten sodium, aqueous sodium chloride is electrolyzed, then the reaction, the product at cathode and the product at anode, like this question they'll ask. Again, I'll repeat the question. Aqueous sodium chloride solution is electrolyzed in a electrolytic container. The product formed at cathode and anode is respectively. They'll ask these two questions. Or the reaction at cathode and anode also they'll ask. So all these type of questions they'll ask based on this application of EDK value products of electrolysis. So now we are going to discuss that. So for example, if you see the product of electrolysis in molten NaCl and aqueous NaCl are different. Very, very important here. You can see here, underline this, molten NaCl is just liquid NaCl. Molten NaCl and aqueous NaCl are different. So in molten NaCl, the electrolyte contains only sodium ions and chlorine ions. So if you electrolyze molten NaCl, you will get only NaCl dissociates from Na plus and Cl minus. And the reactions at cathode and anode are given by 2Cl minus changes to Cl2. So chlorine gas is formed at cathode, anode, and sodium metal is formed at cathode. So so this is only if you take molten NaCl. Now if you take aqueous NaCl into consideration, then it is different. So we'll see now what happens when aqueous NaCl is electrolyzed. So in case of aqueous NaCl, along with sodium and chlorine ions, apart from sodium and chlorine ions, we'll get H plus and OH minus ions also. And water also will exist because aqueous means water. At at cathode, two reactions complete with each other. That is hydrogen and sodium. And in between means here at the cathode we have two cations. What are those? Na plus and H plus. And at anode also two anions. So which one will go? Only one cation will go and deposit at the electrode. So definitely the one which is having electrode potential value less, that will go and deposit first. Means here negative, no need to see only sign. We have to see only the values. So in between sodium and hydrogen, means in simple words you can say the metal or the element which is placed low in the electrochemical series will go and deposit first. Since higher reduction potential is of hydrogen and it gets preferentially reduced at cathode. So EDK of sodium is equal to 2.7 minus 2.7 and EDK of hydrogen is equal to 0.0. So naturally H plus ions will go and deposit at cathode and it gets converted into by gaining electron they get converted into hydrogen gas. So sodium will be in the solution only. Sodium ions will be in the solution only. That is in the electrolyte only. Very, very important. And in case of non-metals, OH minus and Cl minus. That also we'll see now. So in case of non-metals, that is at anode, two oxidation reactions will compete with each other. That is Cl minus and water changes to oxygen gas. And EDK value, it is 1.36 and it is 1.23. Since the oxidation potential of chloride is more, it gets preferentially oxidized at anode. So oxidation potential, we have to see the oxidation potential, and the oxidation potential of chloride ion is more, so it eventually get oxidized at anode. So chlorine gas is formed at anode. So the product of electrolysis of aqueous NaCl are hydrogen at cathode and chlorine at anode. Underline this: hydrogen at cathode, hydrogen at cathode, and chlorine at anode. So this is very, very important. So if you take molten NaCl, the products are different. If you take aqueous NaCl, the products are different. So they are computed with respect to electrode potential. Sometimes they will not give in the examination. Usually they will not give electrode potential values in the examination. So to remember that, I'm adding a new slide. I'll give one sentence. You just note it down. So for this, I'm adding a new slide. New slide. So in case of products at cathode and anode, first point number one, if two cations are present, if two cations are formed in a solution, if two cations are formed after electrolysis, these notes you have to write down in your classwork. Then the cation which is low in the electrochemical series, then the cation which is low, because they will not give EDK values. If they have given EDK values, easily you can compare and write, as in the previous case. If they are not, generally they will not give EDK values. So simply the cation which is low in the electrochemical series, means here, which is having strongest reducing potential, weakest reducing potential. So low in the electrochemical series will go and deposit first. Will go and deposit. Will go and deposit at cathode. At cathode. So example, when zinc Zn plus 2 Zn plus 2 and H plus is there. H plus will go into deposit first. H plus will go into deposit first. So this in case of cations. So when H plus goes to cathode, it gains electron and forms hydrogen gas. So zinc ions will be in the container only, half hydrogen. So if they are given the values, by seeing the values, you can compare like how I explained the previously, that is EDK of cell. But if they are not given the electrode potential values of the individual cells, so straight away you can use this sentence. If two cations are formed after electrolysis, then the cation which is low in the electrochemical series will go and deposit first at cathode, right? Next, in case of two anions, if two anions are formed, so generally this case will occur only if we take with aqueous solutions. So if two anions are formed, if two anions are formed, the anions which has lower oxygen state, which has lower oxygen state will go and report first, which has lower oxidation state. This is for our understanding, which has lower oxidation state will go and report first. If the anion contains radical, first element you have to compare. We'll go and deposit first. We'll go and deposit. So example, in between sulfate ions and OH minus ions, because from water we'll get OH minus ions, and from zinc sulfate if we take sulfate ions and OH minus ions. So the oxygen state of sulfur is +6. Top oxygen state of sulfur is +6 and oxygen is -2. Already we know it. So OH minus ions will go to anode instead of sulfate ions. Sulfate ions will remain in the solution only. When OH minus ions goes to anode, the product is oxygen. The product is what? Oxygen. Similarly, when H plus ions will go to cathode, the product is hydrogen. So OH minus ions is deposited at anode, which changes to oxygen gas. So they form OH minus changes to oxygen gas, O2. O2 gives rise to O2, that's all. So I hope this is clear. So if two anions are formed, we have to see the oxygen state, and the oxygen state which has lower oxygen state will go into deposit first. And suppose in case of in the previous see also we in the previous section we have seen chlorine and OH minus. Cl minus means oxygen state of Cl is -1, whereas the oxygen state of OH oxygen is -2. Just forgetting -1 and 2, 1 is lesser, so chlorine will go into deposit first in between OH minus. When chlorine ions move to anode, it forms chlorine gas. I hope it is clear. Next. So these two statements are important for our understanding. Now we'll see electrolysis of aqueous silver nitrate. Very, very important. Aqueous silver nitrate. So when aqueous silver nitrate is electrolyzed using silver gets reduced at cathode in preference to hydrogen. Why? Because silver is below hydrogen in the electrochemical series. The one which is present below the substance that will go and deposit first. So in the electrochemical series, if you see, hydrogen can displace silver, but silver cannot displace hydrogen. So preferential will be silver. So silver is formed at cathode, and in between nitrate ions and OH minus ions, oxygen will be deposited at anode because nitrogen oxygen state is N is +5 or +6 we'll get. So automatically N is +5 and oxygen is -2. So we can use my statement only. It's better to use my statement so that it is easy to identify because EDK of cell we cannot, they will not give. So when aqueous silver nitrate is electrolyzed, silver gets reduced at cathode in preference to hydrogen and water gets oxidized to give oxygen at anode in preference to nitrate ion. So in case of here also we are getting two anions, two cations. What are those? Just write down. First I write two cations. When aqueous silver nitrate is electrolyzed, we'll get cations, silver plus ions, Ag plus, two cations we are getting Ag plus and H plus. So in between these two, Ag plus will go into deposit because of its position is low in the electrochemical series. Next, in between two anions. Now we have two anions. What are those anions? Anions we have OH minus and NO3 minus. So the oxygen state of nitrogen is +5 and oxygen is -2. So in between oxygen and nitrogen ions, OH minus. When OH minus ions goes to anode, the reaction is 2H2O gives rise to 4H plus O2 plus 4 electrons. So that O2 is formed. So oxygen is formed at anode and at cathode silver is formed instead of hydrogen. So it is clear now, very, very important because this type of question they'll ask in the examination. So what is the product at cathode? What is the product at anode? So electrolysis of aqueous sodium sulfate. Now let us see. So in aqueous sodium sulfate, we have two cations, two anions. What are those? One cation is H plus, another cation is sodium plus. And two anions, one is OH minus, another is OH minus, another is what? We have SO4 2 minus. So I'm writing here two cations. The cations formed after electrolysis of aqueous sodium sulfate becomes Na plus as well as H plus. And anions, we have sulfate ions as well as OH minus ions. SO4 2 minus and OH minus. So in between these two, sodium ion and H plus, already we know H plus will go in deposit. And in between SO4 minus 2 and OH minus, we know OH minus. So the products at cathode will be hydrogen and the products at anode will be oxygen. So that is given here in the equation. You can see 4H plus O2 gives us 2 and here H2 plus 2OH minus. So hydrogen gas is formed at cathode. So I hope it is clear. So identification, whenever they have given aqueous, it is very important. If they have given only molten, simply we can say sodium will be deposited at cathode and sulfur dioxide gas is deposited at anode. If they are given only molten sodium sulfate, if they are given, here I am writing here again, molten sodium sulfate, molten means only liquid sodium sulfate. So sodium is formed at cathode, sodium at cathode, and sulfur dioxide gas, because from sulfate ions, sulfur dioxide gas is formed at anode. So they'll ask like these questions, very, very important. Which is formed at cathode, which is formed at anode, what is the reaction at cathode, what is the reaction at anode. So these are the four types of questions they are going to ask in the examination. Very important concept for objective. So next, next topic in this chapter, what is concentration cell? Concentration cells are the galvanic cells having same electrodes dipped in electrolyte solutions of different concentrations. So they have different concentrations. The EMF of these cells is due to the difference in the concentration of two electrolyte solutions. With the time, concentration tends to become equal in both half cells. So these are nothing but concentration cells. Concentration cells are the galvanic cells which have having same electrodes dipped in the electrolyte solutions of different concentrations. So the EMF of these cells is due to the difference in the concentration of the two electrolyte solution. So if you find the difference between the two concentrations of two electrolyte solutions, you'll get the EMF. So for example, you can see zinc changes to zinc ions C1 and zinc ions changes to zinc C2. So same, depending same, that is zinc. So EMF of the cell is given by E of cell is equal to 0.059 by 2 log of C1 by C2. Same cell, that is zinc plus and zinc plus. So, but different concentrations. So you can use the formula minus 0.0591 by 2 into log of C1 by C2, where C1 is called first concentration of zinc and C2 is called second concentration. You can underline this formula. In case of hydrogen also same. So EMF of the cell is given by E degree of cell is EMF of the cell is equal to minus 0.0591 by 2 into log of C1 by C2. Log of C1 by C2 is important. So same concentration they'll give 2. So Again, here also the same. Cl minus concentration C1, Cl minus concentration C2 minus 0.0591 by 2 log of C2 by C1. For this C2 by C1, why it is C2 by C1? Because here pressure is same. They have given pressure also. This is concentration cell in which the electrode is reversible with respect to anion. Electrode is reversible with respect